previous gas laws too, right? So sulfuryl chloride, we'll just look at our own. We don't have to pass around. SO2Cl2 is highly reactive gaseous compound. When heated, decomposes as follows. Is this balanced?
Yes. Yes.
Looks like it's we have yet to see a problem from these. Again, all these warm-ups are previous questions from previous years. Okay, I've yet to see one that I've given to you where it isn't balanced, but it's a good thing to double check nonetheless to see if they're trying to sneak you in a sneaky problem like that. Anyway, this decomposition is endothermic. We'll see if that matters or not later. Sample of this many grams of that is placed and evacuated. Again, what does evacuated mean?
No air.
There's no air, there's no pressure. In a 1 liter bulb, and the temperature is raised to 375. Now last time, we put a solid in there and we waited for it to outgas and become a gas. Here I'm injecting a gas. So the moment I start putting in that amount of grammage, I should see an increase in pressure. So what would be the pressure in atmospheres if the bulb has no dissociation of this sulfuryl chloride? Okay, meaning when I pump in that much and this doesn't perform its reaction, how much pressure is in there? So what do I do? How can I solve this? Which equations do we have?
We have.
Yeah, let's do a quiz here to see what information is available to us. We know that its mass equals 3.509 grams. We know that its volume is 1 liter. Good. We know its temperature too, 375 Kelvin. I could go on and write the equation itself to affect its decomposition. My initial pressure might matter. 0 atmospheres, maybe. Okay. So for part A at least, one of the unknowns I want to find is that final pressure. So I'm giving you MVT. I'm looking for P. Which equations might be useful here? I heard a suggestion of the ideal gas law. Okay. What might be another useful one? Combined gas law, PV over T. Okay, fair enough. Really, you just need these two. Remember, the other three, Boyle's, Charles, Guy Lucas, are variations of this one, depending what's constant. Okay, so probably one of these gas laws, so let's go ahead and solve. Out of these, let's see here. This one only works when something's constant. What's that something? When my mass is constant. So my initial condition, sure, is 0 atmospheres. I'm increasing my pressure eventually, but the problem is I'm also changing how much mass I have. Yeah.
There's no dissociation of whatever the thing is called. So it would work for the first one.
Okay, so if we argue that I'm injecting that in, sure. I want to know how many atmospheres is. What's my atmospheric pressure when I begin with then? 0. But this is when my mass is 0. My process to go from here to here is changing my mass. So this would not be valid. But PV equals nRT, nothing has to be constant. I can use this guy. I'm looking for P, good. I told you V, I told you T. Let's look up R again. What is its value in probably liter atmospheres per mole Kelvin, since it's asking for an answer in atmospheres? It's like
0.8206.
0.8206?
Yeah. 0.0. 0.08206.
Okay, 0.08206. Okay, so we also know R then also. What's N?
That's moles.
0.2.
Remember moles.
That'd be the moles of my sulfuryl chloride. I only know it's grammage, so how can I convert those two?
Mole Island.
Mole Island, yay! So, To solve this, how many sulfur atoms do I have in my original compound before it dissociates? I have 1 sulfur. If I recall, don't tell me, 32?
Yeah, sounds good.
You're just gonna believe me, not double check?
Yeah,
Let's go.
human calculator.
Oxygen, 16 each. I count 2 of them there. That's also gonna be 32. And then finally for chlorines, 35.5.
Yep. Spot on. You should.
Oh,
I was impressing normal chemistry. They would ask what's gold, and I'd say obviously that's atom number 79. You know, what's iron? 23.
Who doesn't know that?
All right, add those together.
I know that.
1 is it
35.
135 grams per mole. Okay, fair enough. If that's my molar mass, I need to, is it multiply or divide the 2? I want to divide the 2, namely the 3.5 when I'm given over that's going to give my answer in moles. That's going to be something super awesome, amazing small, right? Like 0.02?
Yeah.
Again.
Just back.
0.02 what? Well, I wanted a few more digits then.
Well, I got
No, it's just
0.26, but I got
0.025.
0.026.
Yeah.
Okay, I remind you, I would argue we haven't done anything legitimately AP yet.
no.
This is just gas laws from year 1. Okay, so even when you approach a problem, and this is again why I encourage cues, if you declare everything, then maybe you just do skills you learned and are more confident with year 1, and we're still probably gonna get some good partial credit out of it. But in any case, yay, I have found how many moles I need. So now this is known, 1 equation, 1 unknown. I can finally solve this. So my pressure, when I put that in, times 1 liter, equals the number of moles I just found, 0.026. Multiply that by that awkward R, 0.08206. Atoms per moles. Do I need to convert my temperature at all? I'm already in Kelvin. Fantastic. Alright. So divide by 1 is nice. 0.026 times 0.08206 times 375.
I got 0.8.
I get 0.8 also.
8 with a bunch of zeros.
0.800 atmospheres.